Yeah, so now we actually have to go through very ugly competitions. There are a couple ways to introduce the notion of the geodesics. One is we try to understand shortest passes between 2 points on the surface. Then we find equations that characterize those shortest passes, and then those curves determined by those equations are called the geodesics. Or you can just define geodesics using the geodesic curvature, okay? And that's another, they're equivalent, but it's two different ways to define the geodesics. I think more geometrically, you should define the geodesics as a shortest pass or locally minimizing curve. Okay, in some books, this is defined in the this is defined using shortest passes. Okay, right. So that's two definitions. Okay, definition one. Okay, a unit. We always assume this has unit speed, and unit speed curves okay, unit speed curve on a surface is called a geodesic if the geodesic curvature is 0. And then you can find two equations which can characterize this equation. Okay, so if this is the first definition about geodesics. In some books, there's another definition. Okay, a unit speed curve on a surface is called a geodesic if it is locally minimizing. Now, what does that mean? Locally minimizing in the following sense. In the following sense, that for every, here's a surface, okay? This is a curve. Locally minimizing is for every point, okay? Okay, so this is I'm going to call this geodesic, right? For any point, T equals gamma S0, okay? There is a small number, positive number, right? Such that this gamma defined on the interval S0 minus C0, S0 plus C0, as the shortest length among all curves, okay? Joining this point gamma and the other point. Okay, so what does that mean? So you have 2 points, and so this one has the shortest length among all the curves joining these 2 points. Okay, these 2 points is one is gamma S0 plus epsilon, and this is gamma S0 minus epsilon. Okay, that's called a locally minimized. Okay, but you have to assume that it's very small piece must have the minimum length. Because that is another way more geometric definition of geodesics. Now, locally minimizing does not mean globally minimizing. Okay, so let's look at this example here as a sphere. Okay, example. Okay, this is a unit sphere. Okay, this is the North Pole and the South Pole. PQ and North Pole and the South Pole. Okay, so the great circle along this, okay, and this is actually global minimized. Okay, so any gamma, any great circle from P to Q, okay, has a minimal, any piece of that actually, any piece of that has a minimal, has a shortest length among all the curves joining it. Okay, I think it's easy to see that. We can look at later. But if you look at the point P here as a great circle, starting from here all the way to here, okay, passing the source pole, and that part of the great circle is still called geodesic, but it does not have a minimum length. Okay, the reason is you can go all around. You can look from here to here. There's another one even short than this great circle. This portion of the great circle. Okay, so the gamma, okay, the gamma from P to Q prime does not have a minimum length. Does not have a minimum length. Okay, or shortest length. Okay, so there's another one from P to Q prime on the other side. Okay, even shorter. Okay, but if we choose, but this gamma is still geodesic, okay, according to definition, because for every point, as long as the distance between, this is between those 2 points are less than pi, then it has a minimal length, okay, among all the curves, okay. So this gamma is a geodesic. Yes, this is a good example to understand, okay. So gamma is a geodesic because at every point, any piece of any portion of this curve, any portion of this great circle, if the length is less than pi or equal to pi, then it has a shortest length among all the curves joining those 2 points. Okay, so this is a simple fact for the great circles on the sphere, okay, on the unit sphere. Yeah, any portion of a great circle on the unit sphere, okay, any portion of a circle has the shortest length if its length is less than equal to pi. Okay. If it's longer than pi, that portion of the circle does not have the shortest length because the other side even shorter. Okay, other portion of the great circle is shorter. So that's now the main theory in this in this section. It says those 2 definitions are equivalent. Okay. So the main theme, definition 1 is equivalent to definition 2. Okay. So if G is 0, if a geodesic curvature is 0, then it is locally minimizing. And conversely, if it's locally minimizing, and then geodesic curvature must be 0. Okay. Well, I will only give you the explanation. I think I'm going to give this explanation here. Okay, I'm going to prove this part. So it has a locally minimizing curve. Yeah, if the curve is minimized, locally minimizing, then the geodesic curvature must be zero. Okay, we assume that gamma, let's say just assume this, okay, on the sphere, okay, a unit speed curve gamma on the sphere has shortest length, okay, among all the curves joining two endpoints. Okay, we just assume that. Okay, locally minimum, you can take a small piece. This is we just assume that piece. Okay, P and Q. So I want to prove that portion. Okay, I want to prove that the curvature is zero. The geodesic curvature is zero. And conversely, if geodesic curvature is zero, then yeah, it's not easy to prove. Okay, you have to develop, prove some other theorems in order to prove this one. Then it must be locally minimized. Okay, so that's not easy to prove. I just want to prove this one, geodesic curvature is zero. Okay, today. But yeah, my microphone accident touched it. Okay, I just see the message. Sorry for that. Okay. So let me go back a little bit. Okay. So we're trying to prove these two definitions equivalent. Okay. The first definition for geodesics, just geodesic curvature is 0. A unit speed curve is called a geodesic. Is called geodesic if it's geodesic curvature 0. Another definition in textbook, other textbook is a unit speed curve on the surface is called a geodesic if it is locally minimizing. Okay, and actually those two definitions are equivalent. Okay, actually those two definitions are equivalent. But what I want to prove here today is if a unit speed curve is locally minimizing, okay, then geodesic curvature must be 0. So what I'm trying to do is I take a small piece, okay, take a small piece, and that's small enough. It's contained in the it's covered by a surface patch, okay, and it has the shortest length among all the curves joining those two endpoints. Join its two endpoints, okay, and I want to show that the geodesic curvature is going to be 0. Okay, the geodesic curvature is going to be 0. All right. And the curve can be expressed in this form because it's this piece of curve is covered by the surface patch. So it can be expressed as gamma s equals sigma us vs. Okay. Yeah. Now, we may consider an arbitrary variation. Okay, so that is a variation is defined in this form, U and S and the V. Okay. Okay. So here tau is smaller than epsilon. Okay. Smaller than, okay, and the S is between A and the B. Okay. We assume that when because here we consider those curves. Okay. So the endpoints UA and the tau, they're always equal to A, okay? And the VA tau is always equal to VA. Okay, it's a fixed point, okay? They're all starting from that point. And VB UB tau is going to be UB, okay? VB tau is going to be VB. Okay, so that means it's independent tau. Okay, if you're on the picture, it shows like that. Okay, this is my original curve. Okay, you have a family of curves among them. Okay, and over here on the surface, the corresponding curve looks like that. Okay, they're starting from P to Q. Okay, consider an arbitrary variation. Okay. Now, then we have we get so-called the variation field. Okay, this is we get a family of we get a geodesics. Okay, a vector field along the curve. Okay, then we get a vector field along the gamma. Yes. Okay, how can I define it? This is defined using this is a W. I call it W. Okay. So I think it's a sigma. Yeah, it's a sigma U tau. And that's a sigma U. Okay. and the second one is okay. By the way, this variation, when I say it's a variation, that means U S tau is always identical to US. VS 0 is identical to VS. Okay, so that means when tau is 0, that's the same coincide with the original curve. Yeah. So this S is between A and B. So yeah, so this curve, the red one, when tau is 0. When tau is not equal to 0, you have other curves. Yeah. From the same point and to the same point. All right, so this is a vector field. Okay, it's a vector field along the curve. Okay, around this curve. So this is a variation field, and when S equals A, that is going to be 0. When S equals B, that is going to be 0. Again, this is surface. This is a curve from P to Q, and you have a bunch of you get a vector field, and so this is a W. Okay, and it has at the two endpoints, this W is going to be 0. But now, for each tau, we get a curve. Okay, that curve is going to be S tau, which is sigma U S tau and the V S tau. Okay, so this is when tau is 0, this is the same as gamma S. Okay, and at the two endpoints, and that's a P, right? And then at the other endpoint, that's a Q. Okay, so you have those two. You have a family of curves. So now I'm going to consider the length function. So this is the length of gamma tau. Okay, so you want to, so this is the length, right? Length function. It depends on, as this is gamma, and here those are lots of curves here. So the length is this is a gamma tau. This is okay. Okay. Yes. All right. So it's gamma S, and so this is a function, and under our assumption, right? Under assumption, by assumption, okay, and gamma, which is gamma here, has the shortest length, right? So that means tau S is greater than or equal to tau Z, right? Right, and so clearly this has this tau S L of tau. This has a minimum value, so this implies it's going to be 0. That's a standard, variation method. So now you have to calculate what is this, right? Can we express it? Okay. Okay, we have to find out this. Okay, I'm going to try to find it. So this is going to be L tau. It's going to be integral from A to B, right? Gamma tau, right? S Yes. This is going to be integral of the yeah. So this is going to be integral of the E, right? And the U, use a function of right now. Use a function of S and the tau. Okay. And when tau equals 0, just U of S. So this I'm going to put T here, okay, instead of this. The length, right? Oh, this is S. So I'm going to use S. Okay. So for simplicity, I'm going to denote this part by G and S tau. Okay, so it's going to be GS tau to the 1/2 ds. Wow. So now you have to do the computation. You have to do the computation. So tau, you differentiate. And that's a tau, right? Okay. So now I'm going to do the calculation. Okay. Partial derivative with respect to tau. When you differentiate, you have to differentiate. So you have to look at the first term, right? So you have to differentiate this EU, right? And EV. Then I'm just calculating the first term. Okay, so remaining is the same. And the plus E and twice. Okay. Right, so this is two parts, right? So if I set tau to be 0, okay, if I set tau to be 0 and I collect those terms, okay, what I can get is the following. What I can get is the following expressions. I have to, yeah, those are the terms here. Yeah, let me. Right. So all I need is just let this to be let copy to 0. Let's go back to this. Okay. I find out after summarize. I collect all the terms here. So I get EU U dot square 2FU U dot V dot plus GU V dot square. Okay. And that's the U and the top. Okay. And that is going to be S and 0. And then the second term, EV, Okay. There are some other terms, twice of this. And the tau and the S. Okay, this is going to be S and 0. Okay, and then plus other two terms, EU dot, FV dot. Okay. Well, this is supposed to be put it here, this, right? So there is a part, yeah, put it here. So then you have to do the integration by part, okay? I needed to look at this g to the -1/2, okay? EU dot FV dot, right? Yeah, I take a look at this. Okay, I look at this term, and I have another term here. I'm going to change it. It's a F and GV dot. Yeah, I'm going to get rid of the second order derivatives, okay? Using integration by parts. Using integration by part, this will be e to the -1/2, g to the -1/2, EU dot, FV dot. Okay. And the plus the second term of so this will be the a little bit. So this will be at the two end points. And then that's the integration by parts. And this is integral. And I think that will be just the derivative. Yeah, that's just a derivative of S. Yeah, that's in the partial. And another term. Yeah, that's it. Now, what I want to say that this part is going to be 0 because we fixed two endpoints. Because this derivative 0, that the derivative 0 when S equals A and S equals B. So you only have those two terms left. Yeah, let me copy it. And plus, so it's pretty ugly, right? The computation. And ds, okay? So this is just about this part, the integral of this part. Let's go back to, go back to our computation here. You see, this we just take care of this part. Okay, we just take care of this part when they integrate. Okay, now by assumption, this is going to be 1. Okay, by assumption, this is going to be 1. So by assumption, it's unit speed. Unit speed implies GS0 is always equal 1. Okay, so put everything into the formula for the derivative. right? We got the integral of a and b, right? And the u, right? Capital U and the capital V here, right? Yes. Now, what is this is actually S0, power is 0, right? S0. Now, what is U? U, because we assume that it's only the one, right? U is half of, okay, EU dot plus 2F U and U dot V dot plus GVV dot square, okay? And the minus right? And another term, EV U dot square and 2FV U dot V dot and GVV dot and minus GS EV dot F at FU and GV. Okay, so look at this. Look at this. Okay? And we know that this is arbitrary, right? This is arbitrary. So you can choose a variation of the field such that we may choose, we may choose U S tau such that US is going to be U, okay? Yes, this is U. And so if you put that, then you will see it's U squared plus V squared. Then L prime is going to be integral from AB, US squared, VS squared, VS equals 0. That implies, this implies US equals 0, VS equals 0, okay? So every locally minimizing curve, okay, must satisfy these two equations. But these two equations is nothing but those two equations. We already proved that these two equations are equivalent to the geodesic curvature 0. Okay, we already proved that geodesic curvature 0. Okay. Yeah. So this is one of the stems in section 9. In section 9.2. Okay. So C section 9.2. Okay. So do we show that locally minimizing curve, okay? And this one, locally minimizing curve, the variation formula after you use a integration by parts, and you get this. Since this two and arbitrary, so this is going to be 0, right? If only if UV must be 0. That's the idea. Okay. Now, so that means, then you get this to 0, and this is nothing but the geodesic curvature equivalent to geodesic curvature. Okay. So we got, we find out locally minimizing curve must have a 0 geodesic curvature. Okay, and they're uniquely, because of those geodesic curvature, those equations. You can see that geodesics are uniquely determined by the direction and the one point. Okay. Okay. So we can characterize this locally minimized geodesic, locally minimized curves by two partial differential equations. Okay. And those two equations are here. Okay. Those are the two equations. Okay. In other words, okay. minimizing unit speed curves can be characterized by v equals 0 and v equals 0. And this is nothing but those two equations. U dot f u dot, and that is going to be half of u dot square, f twice of u dot v dot, and g u v dot square. Okay, and similarly, okay. And we already know that these two equations are equivalent to the geodesic curvature must be 0. Okay, so this is a good theorem, you know. The computation is very complicated. It's just called the variation method. Okay, and actually, in reality, is that we don't have the geodesic curvature first. We have those equations first, and we're trying to understand those curves are locally minimized. Okay, and then using variation method, we derive the four equations, and those are the equations satisfied by those curves. Okay. Then, of course, mathematicians have to prove that if the curve satisfies these equations, then one can show that must be locally minimizing. Okay, that proof takes a little bit more time. It's not that obvious. And those are about the geodesics. Right. So now I'm going to briefly look at the geodesics on the we call that, right? Geodesics on a surface of revolution. Okay, geodesics on the surface of a revolution. That's a typical picture. Right. So those are the geodesics, right? Okay. By definition, if you have a curve, okay, so those curves, we imagine, you know, it's obvious, right? So if suppose this is the shortest loop, why this must be geodesic? Because if it's the shortest loop, right? And I can, you know, if we have already proved the equivalence between the definition 1 and definition 2, then it's easy to see the shortest loop as shortest circle, okay, must be geodesic. The reason is taking the 2 points close enough on this closed curve, then join an arbitrary curve joins these 2 points. The arbitrary curve must have a longer length than that one. Otherwise, you can have a shorter loop, right? Since you already know that this is the shortest loop, so locally must be minimizing, okay? Locally must be minimized, so that's why it must be geodesic, okay? So before you do the calculation, you know ahead of time it must be geodesic, okay? Now the difficult part is about the meridian. Why is the meridian is a geodesic, okay? Why is the meridian is a geodesic? And that's not easy to see, right? Because I think if you draw the picture like that, it's not easy to see. But by the symmetry of this, it's kind of symmetry of this surface. So if those 2 points are close enough, you cannot, but it's not easy to see, you cannot find the shorter path joins those 2 points, okay? And you cannot find a short path join those 2 points. Maybe you can use a bottom for the flowers. You can take a look at, okay? Maybe you can understand better why the meridian, if it's like a small piece of meridian, not a large one, why you cannot find a shorter path joins those 2 endpoints, okay? And I think it's from the, if we look at the flower, the bottom for the flowers, it's the surface of a low resolution, and I think it's easy to figure it out. Okay, but on the other hand, there's plenty of geodesics there. You know, take 2 points, right? If you are able to find the path, this shortest path, then this must be geodesic. Okay, the question is how do you find the shortest path? Okay, from P to Q. So the idea is, we already put it in the last class, is going to be the angle, okay? The angle, the angle, this angle, phi, right? And the rho times sine phi is going to be constant. Okay, that's how do we check whether the curve is a minimum, is a geodesic, right? So that theorem is not trivial, you know, but was discovered by a French mathematician. That's why the theorem is a name after him, right? So that is the sine phi, right? Rho and the sine phi is constant. Okay, that's how do you check whether the given curve is a geodesic, right? On the surface, it's not easy to figure out. Okay, I give you an arbitrary 2 point. It's not easy to find out a geodesic joining P and Q, but we know that the meridian is. Okay, so on the surface, now it's clear. On the surface, in any direction, on a surface, right, on a surface, in any direction, okay, there is a unique geodesic going out, okay, for any vector v at the point P. Okay, we know that there's a unique geodesic. Okay, there's a unique, for any unit vector, there's unique geodesic, okay, gamma, such that the gamma dot 0 is going to be in that direction. All right, so actually there are plenty of that. If the point Q is so close, what I'm going to do, how can I find the geodesic? So what I'm going to do is I look at the around, you know, all the geodesics going out from this point. Eventually, okay, you find the one from P and passes through Q, because all the geodesics coming out right from the point, supposed to cover the whole surface, okay? So that's why if you pick up a point close to P, then you should find a geodesic. You should find a geodesic, okay, coming from P and pass through the point Q, right? Pass through the point Q, okay? So that's why how do we find a geodesic between 2 points? This is not easy, you know, given 2 points, whether there's a, you know, how do you find a geodesic from P to Q? Sometimes the geodesic does not exist. So the surface, if it's broken, there's a hole there. And then you cannot, there's no such geodesics, okay? So But when Q is close to P, yes. But when Q is far away from P, maybe there's no such. Yeah. So if Q is close to P, then there is a geodesic. Then there is a geodesic gamma from P to Q. Okay. If Q is far away from P, then sometimes there is no such geodesics. Okay, it cannot reach to that point. Then there might not be a geodesic from P to Q. And I'll give you an example. And this is a R2, and I delete a hole. Okay, this hole is deleted. Okay, and this is a point P. If Q is here, and you cannot, you get all the geodesics, right, going out from here. But there's a one never reached to Q if the one point to that direction along the x-axis. Okay, because they stop here, end it. Okay, you cannot extend it. But if you choose a Q close to P, somewhere here, yes. But it's a little bit away from P, and then you cannot find the geodesics going from P to Q. Okay. So a surface with a property, you can always find a geodesic from any pair of a point, join any pair of a point, and that surface is called complete. Okay, complete surface. Okay, that surface is not complete. For example, R2 was a delete. Okay, so that's a good example. Okay, to show you. Okay, we're not going to go to completeness of the main surface. Right, and I'm going to have one more lesson trying to explain what Gauss did and his contribution, why it's called Gaussian privilege. Okay, so let me stop here.